All right, good morning, everyone. Welcome to our second class. I think this is where we left off. See if I can, yeah. I think this is where we left off talking about the motion of the stars at night. And the most important fact, single fact about the fixed stars is they are in fixed patterns. So we have the constellation patterns for what they are. And the rotation of the whole sky around the North Star, around Polaris. And the interesting fact, and the very consequential fact, that the stars take not 24 hours to go all the way around from meridian to meridian, but they go around a little bit faster than the sun. The sun takes 24 hours to go around from meridian to meridian, from local noon to local noon. That's what creates our clock. But the stars are a little bit faster. They only take 23 hours and 56 minutes. Now, of course, guys, you realize when I say 23 hours and 56 minutes, I don't mean exactly 24 hours and 56 minutes. There's always decimal points with every measurement, except for the time, actually, at least for many, many centuries, the time it took from the sun to get from meridian to meridian. That was exactly the definition of 24 hours. It no longer is. The people in Boulder and the people in Paris have made improvements on those measurements. But for our purposes, certainly the sun does go from meridian to meridian at noon in 24 hours. And the stars go around a little bit faster, about 4 minutes faster. For us, that's certainly accurate enough. And therefore, the consequence for that, right, is that from night to night, it looks like the stars kind of jump ahead because our clock is dependent upon the sun, which is a 24-hour cycle, and the stars only need 23 hours and 56 minutes to get all the way around. So they can jump ahead 4 more minutes before we say, oh, there's a new night. Midnight has finally arrived. And so that 4 minutes represents 1 degree of rotation. As we learned the whole sky turns around every 15 degrees every hour. And so you do the math on that. That's 60 minutes of arc every hour, 60 minutes. I'm sorry, 15 degrees every 60 minutes. And that comes out to be 1 degree every 4 minutes of time, 1 degree of arc for every 4 minutes of time. So we do have this moving ahead of the, but what we were looking at, and let me go get this and go to Solarium. What we were looking at as we ended was the motion of the moon. So let us go ahead and do that. Let's go here to full screen mode, and let's move ahead here to the nighttime. Here we are today. This is today, and we're moving along, and the day's over, and the sun comes out. And here is the nighttime, and let's take a look again. Remember the idea. Just to review for a second, here we have Jupiter coming up to the meridian. And Jupiter, again, is a planet. It does move from night to night, but it is such a tiny move that in one night, you would never notice it with your naked eye. It's hard to notice it even with an amateur telescope, because it takes 12 years for Jupiter to go all the way around. But the point is, Jupiter will be back here tomorrow night, but it'll be back here after 23 hours and 56 minutes. So actually, if you were to go a full 24 hours, Jupiter would look more, like this. It would have that 1 degree jump. Okay, but we were looking for the moon, and let's see if we can find the moon. Here's our hours. Moon should be around here someplace. I thought I saw the moon. Oh, okay. Let us, moon's got to be somewhere. Here we are. Okay, so here's our moon. We're looking at September 30th, a few days from now. and we see that the moon is in the waning phase. It's following the sun. I'm sorry, the waxing phase is following the sun down after sundown. It is in the growing phase. But what's interesting to us is to see where the moon will be. Here it is at 6 o'clock, 6:30 on the 30th. Let's see where the moon will be. We see it's in Scorpio here. Here's Libra here, and Scorpio here. Here's Sagittarius. Here are the constellations of the Zodiac. We know this is the path that the planets and the sun and the moon take. So here we are in Scorpio, and let us just go a month. Let's go 1 day from the 30th to October 1st. And we see the moon has jumped towards Sagittarius. Going to October 2nd, we're now fully in Sagittarius, and we're now going towards Capricorn. And this is the motion of the moon. In terms of the stars, it moves backwards. Why backwards? Because it's literally moving to the east as opposed to moving to the west. It's going back from its normal motion. All of the normal motion, right, is from east to west. So the moon is moving backwards because the moon is even slower than the sun. Okay, the moon takes an additional 50 minutes to get around from meridian to meridian. So it's just losing time. The stars are just moving ahead of the sun all the time, not by 1 degree each day, but by 12 degrees each day. And that, of course, works out very nicely because how many days is it going to take if you're moving 12 degrees to go 360 degrees? How long will it take you to go all the way around the sky? Well, 12 into 360 is 30. It'll take 30 days for the moon to go all the way around the sky. And so there's our month. Okay, so that's where we left off. Let's go back to our presentation and take a look at the moon for a few slides here. So the moon moves 12 degrees every day, every 24 hours. Well, that's a half a degree every hour. Well, it just turns out by wonderful coincidence that that's the size of the moon in the sky. The moon is a half a degree of arc in the sky. And the moon moves a half a degree every hour. The moon moves its diameter every hour. That's how fast it moves. So here's a beautiful picture of the moon about to occult Jupiter, about to hide Jupiter. The moon hides everything in its path. Clearly, the moon must be the closest thing to the Earth. That was well known to the sky watchers by just looking at how the moon blocks everything as it moves along. An hour from now, guys, Jupiter will be on the other side of the moon because the moon will have moved its full diameter. Jupiter, we know, does not move. Not never mind in an hour, doesn't move in a week. So Jupiter is not moving in the sky. Of course, the entire sky is turning every 15 minutes. But notice how we're transitioning. We're talking about motion with respect to the fixed stars. Yeah, we all know that everything is moving, everything is circling around Polaris every 23 hours and 56 minutes. We're beginning to almost ignore that, to take that for granted. We're taking the fixed stars as our backdrop. And the motion we're talking about now, here in our first instance of the motion of the moon, we're talking about the motion of the moon with respect to the fixed stars. As everything is turning around in one big merry-go-round, what is the relative motion of the moon with respect to the fixed stars and the planets? And the moon is moving backwards a half a degree every hour, but that's exactly the diameter of the moon. So an hour from now, the moon will have moved to the east, will have blocked Jupiter for an hour, and Jupiter will be appearing on the other side of the moon in just 1 hour. That's how quickly the moon will move. Here's a wonderful picture of the occultation of Venus. Here we have the very crescent moon, very new crescent moon, and here's Venus. And this is a time lapse here. Every morning is rising in the east. This is in the east. The sun is just back here ready to come up. So we're just about to block everything out with the powerful sun. But right here in dawn, we get a last glimpse of the moon rising and Venus rising. And notice what happens. The moon is moving east. So as the moon rises, it continues to move backwards, right? A half a degree every hour. And it literally, as it moves backwards, it's going to hide Venus. Venus has not changed. It's the moon that's moving backwards. Venus is moving faster than the moon. The moon is slow with respect to the fixed stars, and therefore it seems to move backwards. A video of this looks like this. Here is the moon rising and Venus rising, but the moon can't keep up with Venus. It's moving backwards. It's slower than Venus. So Venus is just moving right into the moon, and there's the occultation. So this again is very consequential, the fact that the stars move around every 23 hours and 56 minutes, but the moon can't keep up. The moon is very, very slow going around from meridian to meridian. Therefore, if you think about it, therefore it moves very quickly backwards because the fixed stars are racing ahead of it every 50 minutes a day. So we take a look at this. Watch the moon. This is the moon from night to night. That's that 12 degrees every night. It'll move. If you come out the same time at night, it'll move 12 degrees from the night before. This is the motion of the moon against the fixed stars. Take a look at Mars. You can see Mars move. Mars moves pretty quickly from night to night. It's quite noticeable visibly, without binoculars or telescope. However, take a look at Jupiter over that same 4 days. No motion at all. Okay. The motion of Jupiter is so slow that you cannot pick it up with your naked eye. Okay? And never mind Saturn. Okay? So Jupiter and Saturn will not move from night to night to the naked eye, but Mars actually will. But Mars is moving very slowly compared to the moon because Mars keeps up with the stars much better. Jupiter and Saturn have no problem. They keep up with the stars very, very well. It takes 30 years for them to get lapped, whereas Mars only takes about 1.5 years. Whereas the moon, moon only takes 30 days to get completely lapped by the stars. And so we have this relatively quick motion of the moon. Just a few more slides about the moon, and I'll take some questions. You'd be surprised how long it took for the sky watchers to finally be convinced that the moon is lit by the sun, that the moon has no light of its own, that it is the light of the sun reflecting off of the moon is what we see. And this took a while for the sky watchers to be convinced of this. Now, when we see it, it's pretty obvious. This is our normal crescent moon going down in the west, and the sun goes down first, the moon comes out, and the moon sets, and you can very much see that it's the moon that's lighting up the sun. And also, the moon will rise in the dawn before the sun, right before the dawn, and the crescent is the other way. The sun is about to come up here in daylight, and we won't see the moon at all, but right before that, in the twilight, it's kind of clear that what's being lit by the moon is actually the sun. That light is coming from exactly where the sun is. But we'll see that it took a while before this was finally established. So, characteristics of the moon, of course, we have the phases of the moon, cycle of going through the different phases of the moon. The moon always shows the same side, okay, like a fixed disk in the sky. We always see the same side of the moon, because as the moon, in fact, seems to go around us, goes around the sky, the moon must be rotated because it's always showing us exactly the same side. Okay, the phases are just what of that side is lit. We always see the same disk. It's just how much of it is lit as the phases go through. And so we have phases. We have the moon will give us some beautiful symmetry, just as we saw with the sun. We have the waxing moon and the waning moon. The waxing as the moon is growing, getting more and more lit, going towards the new moon, going towards the full moon. And then we have the waning moon after the full moon, where it gets smaller and smaller down to the new moon. And again, that symmetry for the waxing crescent moon, that's the moon that we see. The sun goes down and there's the beautiful crescent moon about to go down, an hour or so later, depending on how high up it is. So it follows the sun, to set in the early evening. And so it sets soon after sunset. Whereas the waning moon, it leads in front of the sun. It comes up right before the sun. And so it rises soon before sunrise. The quarter moon is high in the sky at sunset, and it takes quite a long time for it to set. It won't set until midnight when it's on the other side of the sun. Whereas the waning quarter moon will rise after midnight, rise up very, very early, and it'll be very, very high up when the sunrise finally comes. This is the moon that we see up in the sky in the early morning. This is the moon that we can see sometimes weirdly, like at 10 o'clock in the morning. You'll still see the waning moon. The light of the sun is bright enough that it can shine through the atmosphere. And finally, the full moon, we know the full moon rises at sunset because it's on the very opposite side of the sky as the sun, and the full moon is lit, and it'll set at sunrise. The full moon is up for the entire night, being in the opposite of the sun at all times, whereas the new moon is right there with the sun. If it's in the right place, it'll actually block the sun and get an eclipse, but generally it's not blocking the sun directly, but it's not lit. The part that we see is not lit, and that's the dark moon. So it rises at sunrise, it rises with the sun, and it sets at sunset. And again, when you look at these words, they're all quite symmetric to each other. So again, we see a beautiful symmetry, a beautiful order in the sky. And this repeats endlessly over and over again. Okay, so with that business of the 23 hours and 56 minutes, let's again take one more look at the sun. Okay, but before we do that, some questions. Any questions on what we've talked about so far? Okay, so let me talk about the sun. Just as the moon moves backwards relative to the stars, because it's so slow, it's very, very slow, it takes 48 additional minutes to complete that revolution. The sun, right, also takes not 48 minutes, but it takes 4 minutes more to get around. It takes the full 24 hours. Therefore, the sun is also slow like the moon, not as slow, but we could also say, as opposed to the stars jumping ahead of the sun every day, which is absolutely true. The stars do jump ahead on that meridian. That's why we have the winter constellations and the summer constellations. We could just as well say that the sun is moving backwards through the stars, just not as quickly as the moon is. But again, the relative motion, if it can't keep up, if the sun can't keep up, it's going to fall back and fall back and fall back about 1 degree every day, because the stars are jumping ahead of the sun 1 degree every day. It's just simply relative motion. And yeah, if you fall back 1 degree every day, then the sun will move around the entire sky in about 360 days. Well, it turns out it's not actually 1 degree. It's a little bit less than 1 degree. So in fact, it takes 365 days for the sun to fall back all the way around the sky to come back to where it was, wherever you started counting, and that's 365 days. So this is the relative motions of the sun with respect to the stars. Now you may say, well, how do the sky watchers see the motion of the sun with respect to the stars when the sun is out, we don't see the stars? True, fair point. But again, here's a picture right before sunrise, and we see the stars that are that we see just on the horizon right before the sun comes up and blots everything out. And we see that it's Sagittarius. We recognize the constellation Sagittarius coming up, and clearly the sun is in Sagittarius. It's in that constellation somewhere, because a few minutes from now, 15, 20 minutes from now, when the sun is totally up, we won't see Sagittarius anymore, but it's still there. It hasn't disappeared. We know that the sun is in Sagittarius. And then if we look the next day and the next day and the next week and the next month, we will see different constellations that are behind the sun. Here's an evening view. Here we see in June, the sun goes down, and what's the constellation that we first see right on the horizon when the sun gives us a chance to see the stars? We see that Gemini is right above the horizon. So the sun was very close to Gemini here. You wait a couple of months, and when the sun goes down, you won't see Gemini anymore on the horizon, but you'll see Leo. So the sun is moved from one constellation to the other. So the sky watchers can get an idea of how the sun is moving through the sky just by looking at the constellations on the horizon by the sun in sunrise and sunset. Okay. So with that, let's take a look at a better view of that. Let's take a look at the actual motion of the sun. Let me get our full solarium here. And why don't we go back to today? Okay. And what I want to do, I want to get up to the meridian. Let's get up to the meridian here today. Get to local noon. And we'll see where the sun actually is by the magic, of course, of solarium. We see that the sun is in Virgo. Here are the great constellations of the Zodiac. Here's Cancer and Leo and Virgo and Libra. And right now, the sun is in Virgo. Now you may say, but we never see this, right? Except for an eclipse, which happens very rarely. We can't see the stars when the sun is out at noon. So how do the sky watchers know this? Well, think about it. The sky watchers watch the sky for 100 years, 500 years, 1,000 years. They know the entire sky. They have the map of the complete dome of the sky. And so here's the sun, right, at noon on the meridian. Okay, what's going to happen 12 hours from now? 12 hours from now, the sun will be gone and some star will be on the meridian. Okay, so let's wait for midnight and let's wait for some nice bright star to be on the meridian at midnight. Where's the sun? The sun is exactly opposite that star in the chart of the stars, which of course the sky watchers have. They can move around 180 degrees and see exactly where the sun is by knowing what star is on the meridian at midnight. The sun is on the meridian just in the opposite place. And the sky watchers, after a few hundred years, will have no trouble tracking where the sun is by simply tracking the stars on the meridian at midnight being opposite from the sky. So we're really not cheating by having solarium show this. The sky watchers of the ancient times could track the sun that accurately and know that the sun is in Virgo today. Now, let's see what happens as we move a day. Here is the day, here is the time. So here's the 29th, the next day. And let's move one day. Notice that the sun, that the stars are moving, jumping ahead, as we know. The sun is going down. We're going towards the winter. It's staying at local noon, but it is getting lower and lower in the sky. And so we have two ways of interpreting this, guys. We can say that Virgo is jumping ahead of the sun, or we can say that the sun is falling back through Virgo. They are equivalent, right? All motion is relative, but clearly if we think of the stars as this fixed pattern, then the sun is moving backwards in the sense of the sun's normal. Everyone's normal motion is east to west, but the sun is losing ground to the stars, so it's moving literally backwards towards the west. So that's what I mean by moving backwards from the normal rotation, the daily rotation. So if instead of doing this by day, let's go by a month, let's go from October to November. Here we're in Virgo. We should wind up in Libra here by October 8th. And sure enough, we are in Libra. Okay? And we go to December. And here we are between Libra and Sagittarius. And in January, we're fully in Sagittarius, heading towards Capricorn. And in February, we're just beyond Capricorn, moving into Aquarius. Okay? If you know your birth sign, then you should be recognizing where your birthday is as we move through. Going into March, Aquarius, between Aquarius and Pisces. And the sun moves along Pisces, moving up. So the sun follows this path backwards through the sky as the year goes on, because it's losing 1 degree every day with respect to the stars. And we can see what that path is. Let's have Stellarium show us that path. The path of the sun is called the ecliptic. And there is the path of the sun in the sky. Right now it's in Pisces. And if we just go by day, here we are, is the 8th, where are we? We're in July 8th of 2023. We've gone quite in the future, but it's okay. Let's go to the 9th and the 10th. We're going through April. Yeah, the sun is moving along backwards through Pisces, about 1 degree every day, heading towards Taurus, staying on this path. And this path that the sun makes through the sky is called the ecliptic. And it goes all the way around the sky, all the way around the dome of the sky. The sky watchers know this path very, very well. And we're getting very close to the statement that would make sense to us now, that the sun and the moon and everything else goes around the earth. Everything seems to be going around the earth. Everything is going around the full 360 degrees of the fixed stars of the sky. So that's where we're headed with this idea. Okay, let me get out of this, get back to our presentation. Any questions about the motion of the sun through the stars, following a path that's called the ecliptic, and it goes through a certain set of constellations. These constellations obviously are very important in culture because they're the ones that the sun goes through. They're very special. Sure enough, they are special. And so they will have special names. And those are the constellations of the Zodiac. And all cultures of sophisticated sky watchers have mapped the sky this way and know exactly and have names and figures and everything for all the constellations that the sun goes through during the year. Questions about the motion of the sun. This is very, very important that we understand when we talk about the motion of the sun. We're not talking about the motion from morning to night. Yeah, we got that. We know that. That's kind of boring. The sun goes up in the morning, it goes across the sky in the day, and it sets at night, just like the stars, like everybody else. What we're interested in is tracking these 7 planets, as the Greeks call them, the sun, the moon, and the 5 planets that we have, Mercury, Venus, Mars, Jupiter, and Saturn. The 7 planets, how they move with respect to the fixed stars as a backdrop. That's the motion that we're talking about. That's the motion that's going to have to be figured out right up through the time of Newton. This is the great problem that generates the scientific revolution, is to solve this problem, not the problem of rising in the east and setting in the west and going around the earth at night and coming back again. It's this relative motion of the planets with respect to the background stars. The sun has it, to the degree of 1 degree every day. The moon has it to the degree of 12 degrees backwards every day. And we'll see the planets, all hell's going to break loose when we take a look at the 5 planets. Are there any questions about this relative motion of the sun and the moon going backwards through the stars? What I mean by backwards, as opposed to the normal east, moving from east to west, here these little jumps are moving actually eastward, backward through the fixed stars. Any questions about this? Questions or comments? No. Okay.
I guess I have one comment, Peter.
Yes.
Boy, the advent of photography really makes this a lot more easy to understand and appreciate, especially time-lapse photography. But when we talk about the sun having or the moon having apparently moved, that's a lot easier for me to appreciate when I can have a photograph to compare with a photograph taken a month earlier than simply relying on people writing down their impression of where the moon had been.
That is so true. And you will not be surprised, Mike, that the invention of photography in the 1850s, as it developed and got more and more sophisticated through the end of the 19th century, completely revolutionized astronomy. Completely. Okay? One of the great technological changes of astronomy in the late 19th century is, well, there are 2. One is photography, and the other one is to measure the light coming from the stars and be able to break it up into its spectrum and analyzing the spectrum of light. Those 2 things brought us into the modern world of astrophysics. One of the 2 of them being photography. So very, very good point, Mike. Any other comments or questions about the motion of the sun and the moon through the background stars? I want you guys to be comfortable with this idea. And it's not rocket science. It's simply that the sun and the moon can't keep up with the stars. The stars are going around every 23 hours and 56 minutes. The sun's 4 minutes slower. The moon is 50 minutes slower. It's really that simple. It's like running a race. You're watching a race and you see the slow runners being lapped by the leaders. It's really as simple as that. Okay, so we just want to touch upon the motion of the planets today. We'll have a lot more to say about the motion of the planets as we go on. Well, let's just get an introduction to the idea of the 5 planets. Again, the planets have been recognized by all cultures. They are very obvious. They're bright stars, and they move. They move weird. They are not fixed. Matter of fact, the word planet, the Greek root for that is wanderer. Very good name for them. They wander through the background stars. Of course, I'll say this just one more time, and so you won't throw something at me. Of course, the planets are moving from east to west every night. They rise at some point and go across the sky and set at at some point. Of course, they share the entire motion of the sky, as everyone does. That's not the motion we're talking about. The motion we're talking about is the motion of the planets with respect to the background stars. Okay, how do they move with respect as the whole shebang moves? These guys moving literally through that tapestry of the fixed stars. That's what we're talking about. That's our focus. So the nightly motion of the planets, they share, as I say one more time, they share, of course, the motion of the entire starry vault. Here we have the moon going down, and here we have Venus going down, setting, and right after the sunset, going down to the west. So how do we track the planets? Well, the planets are different. They're very different, but they're different at least in two ways immediately that was seen by the sky watchers. One is that the planets are not fixed, that they move. Okay? They move like the sun and the moon, okay? In that sense, they move against the background stars. But boy, do they move. They move very, very differently. The sun and the moon are always moving east. Okay, 1 degree for the sun, 12 degrees for the moon. They're always moving backwards to the east, further and further and further, and they get themselves all the way around the sky in one loop. No problem. Fairly simple. If that was the whole situation, astronomy wouldn't be what it is. This, however, is the motion that we see. Here is the motion of Venus up on top, and here is the motion of Mars down the bottom. This is weird. Okay, so here's Venus moving to the east as it should. Okay, we go from April 1st to May 1st. This is just how the sun would move or the moon would move, just at different speeds. Venus is moving much slower than the moon and the sun, but pretty quickly, pretty good clip. But at some point it'll stop. It'll stop its motion and head backwards. It'll start moving actually from east to west, just the way the whole sky is turning. It'll move like this for a whole bunch of days. Here's June 1st. Here's July 1st. At some point it'll stop and start picking up and going back its normal motion, the motion that we're used to, the motion that the sun and the moon have. This is the path of Venus. Venus does this all the time. It's this wiggle cycle happens as it wiggles across the sky. Here's Mars. Okay. Again, Mars is moving along. If you can see these dates here, this is May 1st, this is June 1st. I think so. Is that right? Yeah, I'm sorry. This is May 1st, May 16th, May 30th. As we move along, again, this is the normal motion that you would think Mars to have. It's moving towards the east, perfectly fine. You would think it would keep going, just like the sun and the moon. No, at certain points stops, turns around, and starts moving backwards to its normal motion. Okay, it's literally continuing on. Here we are in July, and it'll stop again and then continue on, in its normal motion of the. So this weird backwards motion, and again, I'm using the word backwards now in an opposite way, almost a negative of a negative. This is the opposite of its normal motion. Its normal motion is moving to the east. It'll actually move west through the sky for a little while before it'll go back and start doing its regular thing. That regular, again, following the motion of the moon and the sun. This motion backwards, moving towards the west, is called retrograde motion. So the name that it's given. And the planets are not fixed, but they move like this, and they also change their brightness, which is a unique characteristic. Okay, the sun and the moon really do not change their brightness. Don't confuse the phases of the moon with the brightness of the moon. Okay. That the moon is lit up by the same brightness, the brightness of the sun, more or less, certainly to the naked eye, that there's no change to the brightness of the moon, except the fact that more of it is lit. The stars certainly don't change their brightness. Again, with respect to your naked eye, it doesn't change. The stars don't change their brightness, but the planets, yes, very much so. It's very noticeable how change their brightness, particularly Mars, Jupiter, and Saturn. Very dramatic in how they can change their brightness as you watch them go through their cycle. Okay, so let us take a look here at this retrograde. Here's Mercury with that retrograde motion going backwards. So compared to the moon, the planets move slowly through the starry vault, making paths through the fixed stars. Like the moon, the motion is backwards, basically from west to east. That's their normal motion most of the time, but it reverses its direction at different times. And these 5 planets seems to be doing this independently of each other. There doesn't seem to be a lot of rhyme or reason to this. Even if you watch this for a few hundred years, it's very difficult. You can certainly get the pattern of Jupiter, you can get the pattern of Mars, but then they ask, well, what's the connection between the 2 patterns? That's a tough one. That's very, very tough. There doesn't seem to be much of a pattern between Jupiter and Mars. It's got to be one, otherwise we wouldn't have modern science, but it's not easy to see by just looking at these tables. Okay, so the motion through the fixed stars is much slower than that of the moon, and for most of the planets, the motion can't even be detected from one night to the next. Okay? So that's certainly true for Jupiter and Saturn. It's also hard to see Mercury. Mercury is almost always so close to the sun. It's very difficult to see. But if you when you and can see it, you will notice a difference between from night to night. So let us take a look at our final animation here for the stars. I don't know where that sound is coming from. Not sure what's going on here, guys. Let's see. I don't know where the sound is coming from. This is terrible. Can you guys hear this sound, or can only I hear it?
I don't hear a sound.
Good. All right. So I can put up with the craziness. I'm glad. So apparently the sound from YouTube does not come through to the class, which is interesting. I noticed this when I watched the video, the recording after our first class, and the sound of one of the videos did not come through on the recording. Let me see if I can find out. Ah, okay. I had some other window open. Whew. All right. Even now I don't hear the sound. Let's go back here, guys. Let us take a look. Here's Mars coming down, moving to the east very nicely. Here's the sun going down, Mercury going backwards. You see that thing that just flashed by? Watch it again. Boom. that thing, that's the moon. That's how fast the moon travels, because the clock is turning very, very quickly here. Let's take a look at Saturn. Look at Saturn there chugging along, moving backwards. He'll stop. That's his retrograde motion. And now he'll begin to move normally. See, he's moving in the same direction that the moon is moving. This would be the normal motion towards the east. There's Mercury moving towards the east. But Mercury will stop, move backwards, and then start moving forward again, catching up to the sun. But good old Saturn, Father Time, Cronus, he just kind of chugs along. There's the end of, he'll begin his retrograde motions, moving backwards, slowly at first, heading back a bit, and then that will stop after a while, and then he'll start going forward again. It's kind of like 3 steps forward and 2 steps back for Saturn, all very, very slow. This whole thing takes 30 years for Saturn to get all the way around the sky. Notice again, there's Mercury catching up with the sun. We'll probably see Mercury come back a bit. No, we missed it. Okay. And there's the moon, 12 degrees every night, zipping across the sky. Okay, I think I want to go back here. We should see something we want to see here. Yeah, here's Mercury. There's his retrograde loop. Doesn't go too far, though. Doesn't let the sun get too far away from it. There he's catching up to him again, and he'll kind of zoom around, go back and forth around the sun. So there's one characteristic that's different that the sky watchers saw, that Mercury and Venus are always buzzing around the sun, whereas Saturn, Jupiter, and Mars, not at all. They can be anywhere in the sky with respect to the sun. And I think at some point here we will see, here's Mars. I think Mars will go into retrograde here. Maybe not. You're not going to go into retrograde? You're going to keep going where I'm going? All right. There's a nice retrograde of Venus. And here he goes, his normal motion. Okay, I don't know what else we can see here that's new. I thought there was a nice retrograde of Mars. Let's wait a little bit. We only got another minute left to this video. Look up in the corner there. And we should see Mars. There's again Venus ahead of the sun. Mercury ahead of the sun. Here's Mars. Mars will come down, moving normally, and there's that retrograde, a big retrograde motion. It'll disappear from our view, but give it a minute, that retrograde will stop and he'll start going forward again. And there he comes forward. And he has a very, very big, he takes 10 steps forward and 3 steps back. The Mars will just continue right along, just like the sun, just like the moon. Long, long regular motion with a relatively short retrograde. So that is the motion of this of the stars. It is a handful. It's a lot. It's weird. It's hard to get your head around what's going on. But this is the great problem that was posed to the people who began to finally try to make models of the sky. You can handle the fixed stars very easily, right? You can just kind of have them turn around at a constant speed all the time, no big deal. The sun and the moon, at least they don't go into retrograde. They have a certain cycle, a little bit slower, but we can handle that. It was the planets that require go on. Okay, before we start the next presentation, any questions of where we are so far?
Peter, on that previous slide showing the retrograde motion of Mercury.
Yes.
The other thing that struck me is that for the forward motion, the interval from one sample to the next was pretty constant. And then when it switched to retrograde, it shrunk a lot, as though, I mean, as though we were looking at it from an angle or something.
Yeah, there's a lot more to say, Mike. That's a good observation. There's a lot more to say about the planets, as you can imagine. But I don't want to inundate us here with observational astronomy and just get lost in the weeds. So I think we've seen enough of the sky to get a basic idea of what's going on. What's the most important? What is the great takeaway? The great takeaway is that the fixed stars turn around us in a very regular way, and the 7 planets move with respect to the fixed stars. They can't keep up with the fixed stars, and they're generally falling backwards through the fixed stars, except the 5 planets have a mind of their own, and sometimes they move forward through the fixed stars, called the retrograde motion. That's the great takeaway that have to be tackled once you want to start to not move, just once you want to move away from just keeping tables like the Babylonian astronomers, but you actually want to start to create geometric models of what's really going on. Think of these things as little balls in the sky or something or other, and make a geometric model. Okay, then we're going to have to say a lot more about this, and we will. But I think we've covered a good ground, and that is a good observation about the varying sizes of the retrograde loops. Okay, we switch gears here now because we weren't going to move into, really the beginning of all of that, of creating geometric models, and it begins with the Greeks. As I say, the Egyptians and even the Babylonians, with all their data, never actually felt the need to create a realistic, naturalistic, rational geometric model. They just didn't. For one thing, their geometry really wasn't up to the task. Maybe that's a good reason, but they were satisfied with their tables and looking through and seeing regularities in the tables. We'll see it is the Greek culture, the ancient Greek culture, that has the wherewithal, and for some reason, the curiosity, whatever it is, to make this next great step. And it begins with the philosophers. It'll take a little while before we get to real astronomers. Our story will begin with the beginning of philosophy, and very quickly on we'll see, following right after the beginning of philosophy, or actually with the beginning of philosophy, we will see the beginning of abstract mathematics, and that's not a coincidence, as we'll see. And only after those two things are developed will the mathematicians begin to start thinking about building geometric models based upon these philosophical ideas and these philosophical, configurations that the philosophers come up with. Let's get serious about this. Let's try to build a geometric model Only the mathematicians can do that. Once that's done, once the mathematicians take it away from the philosophers and the philosophers fall by the wayside, we have the mathematicians in charge, and now we begin to have the astronomers, because they become the same people. The astronomers and mathematicians are the same people, and those are the first people that we would recognize as true scientists. I'm getting ahead of my story, but that's basically where we're going over the next few lectures. So let's start with the philosophers. Again, the Greeks had a very similar ancient cosmology as well, very similar to all the other ones. Basically, the Earth is flat, somewhere or other surrounded by this primeval sea. And the heavens above, and the underworld below, and it's very similar to the other basic mythical views of the other civilizations around the Greeks in the Mediterranean basis. Here, of course, we have Genesis, the Israeli tribes, and on the Mediterranean basis, with their story of how the world began. Very, very similar, very, very common themes through this. So the Greeks started the same way, with this basic idea. Homer and Hesiod, in their poems, basically put the Earth in this kind of a context, the way the other Mediterranean civilizations did. Where and how does it change is what's interesting. It changes all of a sudden. Homer, the time of Homer is generally about 800 BC. You jump 200 years to 600 BC, and it is this world of the Mediterranean where something amazing happens. Historians of science, intellectual historians, historians of intellectual history, write about this forever. They've been writing about it ever since it happened, or ever since the Romans began having histories of this stuff, and it continues on to this day, to discuss how this happened. But it seemed to happen here in the area of the coast of Turkey, Asia Minor, and the city of Miletus, where kind of a new kind of inquiry began. You could say it's pretty well situated geographically. You've got the Babylonian empires behind it. You've got Egypt directly underneath it. So you've got those two great civilizations with their ability to influence and learn from those civilizations, gather from what those civilizations have to offer in terms of technology, in terms of mathematics, and in terms of the sky watchers. So it's all there for the people in Miletus, and just a certain number of incredible individuals began doing things, began thinking about things in a very, very different way than ever before in the Western world. And I'll say this one more time, just because it is politically incorrect to focus only on the Western world. We are focusing on the Western world because our focus is to understand the scientific revolution. The scientific revolution is a product of Western civilization. Full stop. We don't have to make an apology for that. Okay, the people who created the Western civilization were Europeans. So we're tracing the influence to those people. And as wonderful as the civilization of China and Japan and the Aztecs and the Incas are, and as fascinating as that history is, it had no influence on the scientific revolution. And that is what our focus is. So this is why we are talking about Western civilization only. Okay. End of that. Many people would criticize what I just said as being that's still not enough. You still have to, but we're going to go on. Life is too short to fight over such things. So how did these things start? Who are these individuals? Well, the first one is a very famous guy by the name of Thales of Miletus. Thales is the first person in the history of philosophy. He's the first person in the history of mathematics. He's the first person in the history of science. Thales starts everything off. When you read a history of Western civilization, this guy is the beginning. There are rulers that we certainly know before Thales, rulers of Egypt and of the Mesopotamian civilizations, but they were not intellectual thinkers like like Thales. In fact, no one we have any record of was a thinker like Thales. He just started to ask new kinds of questions. And those questions were things like, what is the fundamental substance that the whole world is made of? Wow. No, the Egyptians and the Babylonians never asked such a question. Okay. Thales is searching for the simplicity in nature, bringing it down to its essentials. Okay. What drives and controls the natural processes? What are these orders that we see? What's driving this stuff? Not just accepted, recorded, but what actually is underneath it? What's behind these symmetries that we see, these orders that we see? These are truly new questions that we don't see in the record, in the written record of the Egyptians and the Babylonians. Okay, maybe somebody walking around the streets asked them, but no one ever wrote them down. And so we have no historical record. Thales is the first one that we have a record that comes down, not actually any record, there are just kind of tidbits and fragments of what he said written down by other people who, record, the history of these things and talk about Thales and what he said and what he taught. This is the first teachings that we have. Thales is responsible for a lot of new stuff. One of them is that he actually took the geometry of the Greeks, of the Egyptians. He traveled to Egypt. We know that. He learned his sophisticated geometry from what the Egyptians had to offer. But what he comes back with, he takes some of the true facts of geometry that the Egyptians knew well, that, for example, when you have an isosceles triangle, when the legs of the triangle are equal, that the base angles are equal. For the first time, Thales writes down a proof for that. He actually shows it doesn't matter what the sides are, that for any isosceles triangle, as long as the two sides are equal, no matter how long they are, then the two base angles will be equal. And this is what is attributed to Thales is the first proof. Now, of course, we're not talking about the sophistication of Euclid yet, where we have postulates and everything, but we have general ideas which we can all agree upon. And he makes an argument. He makes a logical argument to show that if the two sides of the triangle are equal, and based upon general principles that we can all agree on about the geometry, then it must be so that the base angles for those sides are equal. And this is we don't see this in the Egyptian or the Mesopotamian culture. There is no notion of proof. All there are ideas, there are examples, countless examples of important isosceles triangles that are built in their engineering, et cetera, et cetera. The fact is known. The fact is known that if, in fact, the legs of a triangle are equal, the base angles are equal. That statement is certainly true and understood and known. But they didn't seem to feel a need to prove it in the general case. Thales wants to prove it in the general case. This is something truly new in Western civilization. This is a big deal. The idea of proving things. He is famous in his own time in the ancient world because he was said to have been able to predict a solar eclipse. Now, that is a big deal because solar eclipses are very scary. Even in Thales' time, they were scary. And the thought that historians of science have is, again, going to Mesopotamia, which was right behind him, and learning of all of those records, maybe he saw in those patterns, he could see the pattern of these solar eclipses and could predict when the next one would be. Speculation by the historians of science, but he's famous in the ancient world. Oh, Thales, he's the guy who first, predicted. He taught that the Earth was a flat disk floating on the primeval waters, not very far from the picture that we just saw. The water is the primeval substance of the universe, and makes up the bulk of the universe, and we have this flat Earth floating on top of it. And in fact, he went further and said that everything is made out of water. It is the fundamental substance. What? Who needs a fun? The Egyptians and the Babylonians did not need a fundamental substance. There were different substances. That's fine. There's rocks and trees and air and fire, and it's all fine, you know? No, what's the fundamental substance that everything is made out of? What kind of question is that? It is a very new question. Okay? His answer, you may not be very impressed with, is water. Okay, there are better answers, you know, going to quarks, but it's an incredible question. And even the answer is not so bad, right? Because water does take the forms of steam and liquid water and solid ice, and water is so fundamental to our existence and life. No, not a first bad candidate at all. So before we leave Thales, just want to go back to this idea of proof again, guys. We see proof with Thales in the context of mathematics, and of course that's how we think very much of mathematics, of proof, certainly in the realm of science. But if you take a step back, this idea of proof itself is a new concept culturally. You don't see the idea of proof and arguing from evidence and convincing someone else that something is so in the ancient world before the ancient Greeks. There was not this idea in the Egyptian and the Mesopotamian societies. Things were known not because they were proved, they were known because everybody knew them. It was what was common sense. It was clearly what was in front of your eyes, or what in fact was maybe told to you by the king, the pharaoh, or the priests. You either took this information from authority or you took it from just common custom, but you didn't have to, but no one had to prove something to you. You just accepted these things that were true in your society. We don't find this idea of this kind of skepticism and will convince me of this. How are you going to convince me of this? This is a new idea in the Greek culture. This is a big deal. We see it very easily in mathematics as it grows in mathematics, and we'll see very soon with Pythagoras. But it's a wider idea than that. And again, intellectual historians of science will point to the idea of the Greek city-state and the idea of democracy, the idea of not having these, you know, rulers and kings who told you what to believe, that there was a common market of ideas, that there was a dialogue of ideas, that there was a dialogue back and forth, that you had to present evidence to back up your argument, that you had to convince your fellow citizens that what you were saying was a good thing to do, that there were other people who had a different point of view, who could put different arguments, different facts in front of you that would argue for another possible outcome or another reason. This is something we see really in the Greek culture for the first time. This is a very big deal, and of course this will underlie the whole methodology of science, right? The idea of being wrong, the idea of presenting new evidence that can show you that your existing position is wrong, that there's something wrong with your thinking, that there are new facts that we didn't know that have to be considered now. This whole process that we just take for granted was actually invented by the Greeks in this way. It has, you know, been termed by the historians of science and intellectual historians as the intellectual revolution of the Western world, as opposed to the scientific revolution and the industrial revolution and the agricultural revolution. This is the intellectual revolution. This is kind of underpins everything that goes forward. So, okay. Before we look at Thales' student, Anaximander, we'll stop here with Anaximander, say a few words about him. Do we have any questions about so far? Comments, thoughts? Are you still with me? Are we doing okay? All right, I'll take that as a yes. Someone want to unmute themselves and tell me we're doing okay?
I think so.
All right, thank you, Mike. We come to Thales' student, Anaximander, and we have another jump with this guy. This guy brings some new things to the table. Very much a contemporary of Thales, a younger contemporary, student of his. And this really is a school of thought. Again, this is a first. This is the first school of thought that you have a bunch of people, one learned from the other, and students came to learn from them, and they wrote things down, and they were known throughout the ancient world for what their thinking was and their influence. This is all new in the Greek culture, not seen in Western culture before, at least not recognized, not recorded. Not that it may not have existed, but we have no written record of it. It is not historical until we get to the Greeks. So Anaximander, very interesting guy. He was the first one to conceive of an actual mechanical model of the universe. Here we have very radical idea that the Earth is not floating on water, but it's actually suspended in the air. Yeah, the air somehow or other can lift up the Earth. The Earth is still flat. It's kind of like this. It's kind of like a coin, a very thick coin. And the whole thing is suspended, really, in the universe under this primeval air. And the sun, the reason why we can see the sun is because there are certain vents above us where the sunlight can come through. The moon has individual vents, and that's why the phases are, the vents kind of open gradually. And these rational ideas, these rational explanations, they're all wrong, but they are rational, naturalistic ideas and explanations. The gods and the goddesses are gone. Okay, they're not, of course, gone from civilization. They're very much alive and well. They're gone from this tradition of the philosophers. They'll only give lip service to them at this point. Their thoughts are, in the world of the rational, to explain things in a natural kind of a way. So once again, you think about it, if you have the Earth suspended somehow or other, being held up by this primeval air, this gives us the ability to come around the Earth. You can literally physically have the sun and the moon, everybody physically go around the Earth. We're beginning to creep towards a real geometric model here. He's the first person to actually develop a systematic cosmology. Thales, not so much, but we actually have Anaximander. He actually wrote stuff down. Only fragments have survived, but we know from later commentaries that he actually wrote down a treatise explaining his cosmology, how the universe is put together. First time in history, first time in Western history, we have such a document would exist. And the fundamental thing that all matter is created of in the universe is not water, Thales, but it's this kind of abstract thing he called the infinite or the boundless. In Greek, it's the apeiron, is the word that he used. And it's this kind of mystical thing that can take on all different forms and different combinations and create all the different substances that we see. And it is the primeval thing that holds up the Earth. He has a cosmogony, how the Earth began, very different from the myths. He holds that the boundless is, was there eternally from the beginning, and it was being churned up by this eternal motion, these vortexes of motion, and the combination of the motion of turning up the boundless infinity brought into existence the universe as we see it. A combination of this kind of mystical, ethereal substance and motion. Motion, right? The most fundamental thing in all of the universe is motion, as we'll see. We want to talk about motion, we'll talk about the motion of the quarks inside the nucleus. It is the most fundamental thing. It is what makes the universe be. Anaximander has this as his second ingredient. The idea of motion is essential to bringing the universe into being. It's quite amazing, his abstract thinking. Other ideas he begins to make quantitative statements. They're all wrong. He has no evidence for them, but he's taking a stab at making quantitative evidence. The sun is a huge mass, as big as the Earth. This is amazing to think that. It doesn't look that big in the sky, but Anaximander says it's as big as the Earth is. Therefore it must be very far away, right? If it's so small in the sky, but yet it's as big as the Earth. Okay? The sun is the same size as the Earth. It's 27 Earth diameters away. He puts a number to it. It's 27 Earth diameters away. However, the diameter of the Earth is, that disk or floating disk, it's 27 of those away. That's where the sun is. Actually, it's 11,740, but we won't hold that against it. Okay? And the sun is made of fire with these holes and vents, how we can see the sun and all this kind of rationalistic, natural stuff. The moon is also the same size as the Earth. Yeah, the moon and the sun are the same size. Well, they're exactly, in fact, the same size in the sky. The sun is also a half a degree in the skies. That's not a bad thing to say. But the moon is closer than the sun. It's only 18 Earth diameters away. Okay, it's actually 30. But we have beginning of these quantitative statements that are being made about these models. He's the first one to give naturalistic explanations of all the phenomenon that we see, eclipses and wind and rain and thunder and lightning. He has all these rational explanations of changing of the air and the motion of the air. And it's not the gods anymore blowing the winds and Zeus creating thunder and stuff. Those things are gone. Those things are not talked about anymore in these treatises. That's all for the masses. We're trying to explain things in a real way. He's one who introduced the gnomon from Greeks, from the Egyptians. He's the one who gave us the gnomon to the Greek culture, and they, of course, began to do their own sky watching from this, with all the records behind them. Very interesting. He's the first one to be attributed to that he made a map of the entire world. Of course, maps go back much further than this. The Egyptians had maps of their territory, and the Mesopotamian societies had maps both of cities and maps of large territories. And Anaximander tried to make a map of the entire known world. And this is the first time anybody attempted to do this. Why you would need to do this? No one before him, as a record, ever seemed to think that this was actually something that may be very, very useful. And just to finish off with Anaximander, just a kind of a very, very impressive. He has this evolutionary view of living things. Yeah, he is the father of the evolution of life, that the first creatures originated from some kind of moist kind of element created somewhere or other by the Ephion. And man originated from earlier animals, probably fish, he says, because of the moisture business. He figures that man couldn't have just been created whole because babies can't survive by themselves. So, so there must be some kind of evolutionary path where there was always parents and always children, so that children could be nurtured and live to adulthood. So there must have been some kind of an evolutionary path up to what we know now as human beings. Yeah, this is 600 BC. This is Anaximander. This is someone who's, he's working with a different deck here, guys, and we're all learning from him. All of his individual facts are wrong. His mental furniture is quite amazing. Okay, so we will stop there, Anaximander. Any questions before we go? Comments or thoughts? Anybody want to unmute themselves? Okay. Are we doing okay, guys? Is anyone want to make a comment that maybe this is, not, I'm going too fast, too thick, going too slow? Anybody have a comment that can give me some guidance? This was kind of a quiet class, and that's why I asked. Anybody want to volunteer some information, their opinions? Don't be shy. We're all friends here.
I think this is really great.
Well, thank you.
I really do. I
did.
How about the opposite opinion?
It just blows my mind about all of the, I've never studied this before. So it's all new to me, and it's really wonderful. It's
Okay, great. Well,
really
thank you for that.
enlightening. Thank you.
Thank you. Okay, listen, guys, I'm visiting the grandkids in Minneapolis, St. Paul next week, so I'm going to get out the Tuesday email to you on Saturday, probably Saturday night. So I'm not coming back until Wednesday. So look for the email for our next presentation. Actually, we've got this one really to do, but I'm still going to work on it anyway. Keep ahead of myself. So look for my Tuesday email on Saturday night, and see you guys back here next
Have a
Thursday.
great time with your grandchildren.
Thank you. I certainly will. Okay, guys.